Good morning, everyone. This is Srinath from EC section team. Um, in the PTSP, I have chosen the topic the economics of computing whole load aggregation, capacity, utilization, and cost simplification. See, according to the NIST definition, one key characteristics of cloud computing is resource pooling to serve multi consumers using a multi-tenant model with different physical and virtual resources dynamically assigned and reassigned according to consumers' demand. In other words, instead of running in slows workload with the time varying demands on processing intensities are often aggregated, assigned, and provisioned into a shared pool of resources. And one obvious example is cloud computing, where workload says claims processing, shopping carts, and video transcoding from multi customer says insurers, e-commerce companies, and online streaming entertainment firms are aggregated together, mapped to a shared pool of physical resources such as servers, and then execute on those resources. This is similar to the way that lodging needs of travelers are aggregated together. Guests are assigned actual hotel room and then are checked in and moved their luggage up to their room from the duration of their. There are many benefits of this type of aggregation. First, less capacity is typically needed for the pool that were individual to build their own capacity. Second, the utilization of the capacity is greater because the same amount of work is being handled by fewer resources. Thirdly, therefore, the utilization adjusted cost of a unit of sold capacity can be lower. In this issues column, we will quantify those benefits exactly. Aggregation of whole load occurs in many instances in computing. One case is when siloed workloads, each running in their own dedicated capacity, or virtualized and aggregated into a private cloud of dynamically allocated shared resources. Another case is when such private clouds from multi-customers are aggregated into a public cloud. Yet another case is when multi-public clouds are federated to share capacity and capacity requirements. One essential characteristic of the cloud is that available capacity is pooled and dynamically shared to support multi-time varying workload demands. For example, task prepares have peaks in early February and mid-April. Flower sellers have been on Valentine's Day, and Mother's Day retailers have been peak on Cyber Monday or Singles Day, etc. The total capacity that is deployed impacts the total investment requirements of whoever is deploying that capacity. Example, an enterprise for a private cloud or a cloud service providers for a public cloud. The capacity uh, conundrum is that it if there is insufficient capacity, enterprise workloads will either not be run or will run slowly, incurring a cost in labor productivity for i- internal application and or revenue and customer experiences for external ones. If there is excess capacity, it will require an access investment, also incurring a cost through cost of capacity and opportunity cost of idle capital that could be more productively deployed elsewhere. For for cloud service providers, excess capacity means wasted investment, and insufficient capacity implies lost revenue. To quantify this kind of effects, let us model the demands of an independent compute workload as D1 and D2 Dn. To keep things simple, we will assume that or are all identically distributed with mean m and variance s2. Let's further assume that they are normally distributed, although most of the results here apply regardless of distribution. See here, this is a capacity to mu plus 1 sigma. It is a map that has been shown for the capacity set to mu plus 1 sigma. This is about the mu plus 2 sigma capacity graph shown. We aggregated this n demands together. The sum will be normally distributed. It means will be nm and its variance will be ns2, which means that the standard deviation of the sum will be n sigma, whether for one such workload or the totality. We did like to balance availability of compute resources with the cost of compute resources. So generally will be try to find a value of k standard deviations above the mean to set the capacity. For example, for a normally distributed available with mean m and variance s2, the probability that it has a value between m2s and m1s is 0.682689. See here, it is the 100 samples from a normally distributed random variable x with mu equals to mean equals to 10 and variance equals to 2. If we were to examine 16 such workloads in aggregate as shown in figure, we we end up with an aggregated demand that has a mean of 160 and standard deviations of 8, 16 into 2. Thus the coefficient of variance is reduced from 0.252 by 10 to 0.0558 by 160. This is easy to see by comparing figure 3 with figure 4 has scattered plot which is titled. Here 100 samples from a random variable, that is the sum of 16 independent identically distributed normal random variables with mean 10 and sigma 2. See capacity utilization. How the capacity utilization takes place in this. Another important metric is the expected value of utilization of total deployed capacity, which is just the mean demand divided by the total capacity for a single resource, that is 1 mks, and therefore for n unaggregated demands served out of n such resources, it means it's the mean total workload demand divided by the total deployed capacity, or NM. In the case of aggregated workload demands, it's the same total work executed on lesser capacity. So the utilization increases to NN mean, as shown in the figure 5. How workload aggregation monotonically increases to utilization of 100% in the limit as shown. This is the figure 5. Utilization u equals to f of n comma mean comma sigma comma k, where mean equals to 10, sigma equals to 2 for various k from n equals to 1 to 100. It varies. Cloud economics. It is the cloud economics of the given capacity utilization. Summary. What is the summary about this session? Aggregation creates arguable economic benefits in terms of uh, capital investment required for service resource capacity, utilization for the capacity, and the delivered unit cost. These benefits offer a series of advantages for private cloud over siloed resource, public cloud over a private cloud, cloud over fog, fog over devices or things, and so forth. These advantages need to be traded off against other factors, for example response time, data networking cost, etc. Thank you for having this session.